So today we're going to talk about how does a cantilever work. Right? Last time we talked about where cantilevers are used and what they are. Now we're going to learn a little bit about how they work. So we talked about the microcantilever, and it's used in a wide range of applications. Okay, it's flexible and versatile, so it's a common component to a lot of applications. It's not too hard to manufacture. People are always trying to find new things to do with it. So we're going to learn a little bit about the basics of how a cantilever works. Okay, so by the end of this learning module, activity, whatever you want to call it, you should be able to discuss the difference between the static mode of operation and the dynamic mode of operation. Okay? And by the end of the unit, you should be able to know the differences between macrocantilevers and microcantilevers in terms of how they work and what ranges of operation apply. So, okay, a cantilever is a diving board, right? It's fixed on one end, it's loose on the other, constrained at one end, and the other end's free to move. Okay, so cantilevers are built rigidly if you're making a balcony out of it, or flexible. If you're making a diving board or an airplane wing, you want that to be flexible. You don't want your airplane wing snapping off while you're flying. In microsystems, we use flexible cantilevers in a wide variety of applications. Okay, and we can apply an external force or stimulus to make the cantilever flex, and we can detect that flexing and get information based on that. Okay? We can also cause it to flex to turn on a switch, for example. So we can use it as a sensor, and we can also use it as an active switch or an active part, component of a microsystems device. The more rigid a cantilever is, the better it can be used for other applications like transport devices or for a probe. If it's not too loose or too flexible, you can use it for other things, or even a micro latch. People have used cantilevers for latches on micro machines. So you move something into place and it snaps into place. Hey, how you doing, Mary? So there's lots of properties for cantilevers. One of the biggest properties is what material you use. Okay, in this picture we have a piece of oak, perhaps, or some kind of wood. And that wood's very stiff compared to this piece of material, which might be polypropylene or rubber. Right? You wouldn't want to make a rubber diving board. It's not stiff enough. And you fall right off the end of it. You probably would want to make your diving board out of oak. But there might be some application where a rubber diving board structure is useful. So you would pick that material, or some material in between. Okay, so that's part of it. So how much this thing bends in static mode, just hanging out in space, depends on a few things. It depends on what it's made out of. What else does it depend on?
The length.
The length, okay. What else? Width? Could be. Thickness? Could be. Right? Its density, maybe. How thick it is, or heavy it is per unit volume. Its shape.
Force applied to it.
What's that?
Force applied to it.
The force applied to it, yeah, that'll determine how much it bends. Okay, so if you just have it freestanding in gravity, it'll still bend. Different materials will bend a different amount. Also the shape, right? Mm-hmm. Imagine if this, instead of being a plank, was a pipe. Made out of the same material, but in the shape of a pipe. Would it bend the same way? It would be different, right? Depends on the thickness of the wall of the pipe in that case, the diameter of the pipe. The inside and outside diameters will define its shape, its length, of course. So shape also plays a role. So material properties play a role, and the shape also plays a role. Okay? So dimensions, you guys mentioned, length, width, and thickness are important. We're going to talk about mostly the rectangular shape, rectangular cross-section. It's an easier formula to work with and understand. And then if you go on to engineering later, or you start designing something in, say, architecture, right? Or designing a different type of micro device, you might investigate using different shapes to get different responses. So what do you think happens when the cantilever gets short? It's a little bit stiffer. Does that make sense?
It goes faster.
It vibrates faster, yeah? So if it's shorter, it's stiffer. You kind of know that, right? What do the divers do on the diving boards? You ever watch them? They use their foot and they turn this round thing on the side of the diving board to adjust the fulcrum, or where it's allowed to bend. So they might make the diving board effectively a little bit shorter or a little bit longer by moving it. So if they make it shorter, it's a little bit stiffer. What they're trying to do is adjust the stiffness to what kind of dive they want to do and how much they weigh and that sort of thing. So you can change the length of the diving board or the cantilever to change how stiff it is. Okay? So short cantilevers are used like in balconies. Longer ones are used in diving boards. They have diving platforms, which are very short cantilevers and made out of concrete. So there's no spring to it at all. In micro applications, short cantilevers work really well as a latch. They snap into place and stay there. You might make a longer cantilever if you're making a transducer or some kind of sensing device. Okay? So where would you use a short cantilever? Let's review what we just said.
Latch.
Latch, okay. Where else? Where's something we didn't mention? You think of something where a short cantilever would be more useful? I'm trying to
Let us go.
maybe, depending what you're probing, you might want it stiff.
How much of something is there rather than what it is.
Okay, how much something is there rather than
You know what it weighs. You know, when X amount of weight gets there, then something happens.
okay, so you might want to make it stiffer to withstand more force
Yeah.
in an application. That's good. What about like a probe, a neural probe? You may want it stiffer, so you may have to shorten it up. But then if you're trying to go far into the brain, then you need it longer. So you got to do something else to make it stiffer. You make it thicker. Right? Ouch. Yeah, make it thicker, it'll hurt you. So, you know, you've got to balance these things. Okay, so in a macro application, that's large scale, where would we use a long cantilever?
And macro.
Yeah, something big.
Diving board.
Diving board, yeah. Pole vault,
Flagpole.
flagpole. Oh yeah, that's a really long one.
Maybe so.
Radio tower. What's that?
Yeah, I was.
Oh, you were going to say radio tower? I beat you to it. Sorry.
Buildings are that way. You're in the top of a tall building.
Yeah, building.
Those things do move.
Crane.
Crane.
Yeah.
That's a real long cantilever. You got to be careful with cranes, right? Get a lot of torque on them. So what about small ones? We talked about latching devices already. So a shorter one is probably a better latching device than a longer one. Okay, if you want to snap something into place. Okay? What about the width? When would I use a wide one compared to a narrow one? Any
You might
ideas?
need to test something with a larger sample.
Okay, so if you were using it to test for things, would you want a wider one or a narrow one?
Put a flow
More
meter.
sensitive.
Narrower might be more sensitive.
For wider one, you would use it for like if you're using a transducer or something like that. You have more surface area for the material width.
Good. So you might want a wider one so you can collect more stuff.
Yeah.
Might be
How
more
about
area.
and a
to
flow
sense
meter?
it. Good.
You know, a flow meter.
With a flow meter?
Yeah.
Yeah, if it's wider, it would react to the flow. If it's
Yeah, you don't want
airflow
it
or
to
fluid.
overreact, but you still want it
So you can adjust the width depending on what type of flow rates you're looking for.
to.
That's good. If you're going to use it for maybe like a nanobot and make little oars out of the cantilevers and swim with something, you might have to change the width depending on the viscosity of the fluid. If you're trying to power your nanobots in blood or in water or in air.
I just got a picture, you know, of a Roman trireme.
There you go, a little Roman ship where you get 100 orsmen. Yeah. Well, you could make a micro bot that's powered that way.
You know, like the flagella and the bacteria?
Yeah, flagella and bacteria. I think that's more rotary,
That's rotary.
Yeah.
but they've made rotary systems
Pretty cool.
too. So you can, yeah, the chemistry to make something go in a circle is pretty tough. We used to say man created the wheel,
Uh-huh.
but then they discovered the flagella and that it actually rotates.
It's actually a motor. Huh?
And it's a little chemical motor that rotates the flagella, so nature beat us to the wheel.
Yeah.
Because before that, they couldn't find an example of a wheel, of a rotary thing in nature. So they looked at the flagella. Now they may have found some other things. So. Cool. So where are they used? Well, they're used in MEMS. Microcantilevers are used in MEMS. Atomic force microscopes. They have a cantilever with a tip on the end, and they throw the end or the surface of a material. It's very similar to those of us who are older that might know what a record player is and a stylus, right?
Yeah.
Cartridge. Used to have a cantilever on the end, a little point that would ride in the vinyl track and vibrate and change that mechanical motion into an electrical signal in stereo or quadraphonic. I don't know if you know how an old record player works? Have you seen those? Yeah. Have you seen that? Yeah. Good, I'm glad. Because there's a lot of cool mechanical stuff in the record player.
How many grooves does a record have on it?
Lots. Lots of grooves on a record. Well, it has one.
Yeah, well, one on each side.
Yeah. It's a spiral groove. But if you look at...
It doesn't look like
No,
it.
you're right. You're right. It has one long groove. What else? We can use them as a chemical sensor array. We learned about that in the applications lecture. Read-write storage devices such as the millipede, and I think the other one is called the nano storage or nano. What's that?
Oh.
The mechanical storage.
Yeah, there's a nano something. They call it nano storage. I think.
They just have holes in it. Actually,
Yeah.
cantilever. So
It uses a cantilever to make divots. Actually, it uses lots of cantilevers, right? So you can get.
Is that like what
I
Damon was
follow.
talking about? Yeah.
Pardon me?
Is that like what, sort of like what Damon was talking about when he said we can do all these little dots? You know, instead of writing them as letters, you could write them in binary or whatever.
Yeah, you can write characters in other representations, like binary code, sure. And that's how you would do it with a mechanical read-write storage system. It's like Braille.
Oh,
Braille are a series of dots and lines.
what's called
The old pianos from,
Oh yeah, the old player pianos.
Or the music boxes.
they have holes under it.
Yeah, they used to
the
do
music
ticker
boxes.
tape.
Yeah.
Ticker
Remember the
tape.
music boxes? The
Music
ones
boxes.
that you
Same
sing?
concept, huh?
Yeah.
Yeah, so you can look at old school, you know, technology and say, okay, what can I do with that if I shrink it down? And I come up with a device. Right? So maybe we can store music or video onto a systems that are more mechanical in a smaller space.
Matt, what's that one they're using with, I remember something about it being used on airplane wings or something. Or they had an idea for using them on wings, something from them.
Oh yeah, there was a. That's a good suggestion. Some folks made Microcantilever flaps, very small flaps. You can't see them. They spread them over the surface, hundreds of them, over the surface of a model airplane. Actually, it was like a 1/8 scale F-16. Had a jet and everything. And they covered the wings with these microcantilevers, and they actually were able to fly it without using a rudder or traditional, what do they call them? Flaps.
Control surfaces.
So they didn't
That's the way a
really-
V2 flies. It's actually called a fly-by-wire system. And what they do is what's called wing warping. And
Well, this is different than wing warping.
you know, and
What this is they change the surface of the wing
the whole contour.
by making the micro cantilever stand up, causing turbulence, right? Destroying the airfoil on part of the wing, and you can get it to turn.
Yeah.
So they can get it to turn on a dime. So now they're thinking, okay, if you coat the sides of trucks with this, and you're driving down the highway and you get buffeted with turbulence, if you have a smart skin, you can change that skin so that you get better dash numbers. Okay, now, of course, that would be very expensive to build today, but in the future, it might be very inexpensive to do. Once you get the computer power and you get the actuators working and all that. So that's something that's not on here, okay, as an application, but kind of like a smart skin.
Like, is this going to maybe follow Moore's law, perhaps?
Yeah, it will follow something like Moore's law as we develop components and devices and make them cheaper. We'll be able to integrate more of them. For example, they now have pico projectors, which is like the digital mirror device projector, the DLP projector we have now, but they have them that fit inside of a cell phone. So you can project images onto a wall with your cell phone that are about the size of a sheet of paper, maybe a little bigger, and fairly bright. They don't use a halogen light source and a color wheel. They use, I think one's a laser and 2 LEDs, 3 different colors. Okay, that's one technology. They probably have a dozen out there. So they're called pico projectors, and you can go to the TI website and look at it. Microvision has their version of it, where they use one mirror to make the image. It's kind of interesting. So, like you said, Steve, you know, we're building all of these little components better and faster and cheaper all the time. It does follow a Moore's law kind of curve trajectory with respect to cost, right, and integrating capabilities. So you see more and more of these gadgets inside of like a cell phone, an iPod, an iPhone device. They're even getting away from calling iPhones a phone. Now it's a personal interface. What is it?
Communicator.
Yeah, it's some. They have some other system now because it's like a computer.
Like a PDA.
No, it's not a personal data system. It's more advanced than that.
Yeah, it's kind of like.
So it's a communication device, it's an internet surfing device, it's a computer, projection system, it's a camera, right? Audio
Yeah.
player.
I've heard of a couple of phones, maybe several months ago or a year ago, that they actually project a movie on somebody's screen.
Yeah.
So,
Yeah, the Pico projectors are getting in there. They sell them in Singapore. The phones with the projectors built in.
Some
They haven't come.
computers with the projects the keyboard on the smart surface.
Oh, those are cool.
I have seen
Yeah.
that.
Yeah, they project the
Yeah.
keyboard on the
Yeah.
surface and then you just type on your desk. There's no keyboard there, but the scanning red laser it scans real fast, so the keyboard looks like it's stable, right? But when your finger gets in the way of it, it knows which virtual key you're pressing.
It's
I
like
think
they
you
have
can call
a,
it pressing, but.
I can't remember who's doing it, but like a 3D model of the car, and you know, for concept designs, and you could touch the hologram and move a component or open the hood, and
That's along the same line. So you have a 3D representation of a mechanical device, a car, and you can open and close it and look underneath it. They have heads-up displays like that. Toyota uses them, I think. Maybe Honda. They put the repair manuals on a heads-up display for the technicians, so they can. It's displayed on a type of like safety glass that you can look at, so you can see the schematic of the engine while you're working on it. You flip through the pages. I don't know how you do that, but you can actually look at the parts and where they are and what they're called as you're working on the machine or on the car. So rather than having a technician having to walk back, pull the right manual off the shelf, go flip through the pages to try to figure out how to replace a part, it's all there for them. Heads-up display while they're actually working on it. So they're trying to make people more efficient. There's a really good book by Michael Crichton called Airframe, where they talk about a plane that goes down, and they talk about these heads-up displays in the aircraft companies, so they can look at the wiring, they can look at all the different things as they're building the plane to make sure they're doing it right.
Our aircraft have
But now they've done that for aircraft to start with, because aircraft are expensive to build, right? And you have to do it right. Now they do it for cars. All right, let's get back on cantilevers. We've got, we can operate them in static or dynamic mode. So static is when they're not moving, dynamic is when they're moving. So it's kind of like someone who can't see uses a cane and he's tapping to find out what the environment is. That would be a dynamic mode of operation. And static would be the cantilever isn't moving, it just bends. It responds to some stimulus by bending. And you can detect the bending in multiple ways. Okay? So you've got static and you got dynamic. And we use both modes of operation with microcantilevers. There's a picture of static mode. There's more mass, more force on this upper diving board than on this lower one. So if all else being the same, if you have the same diving board, same materials, same dimensions, you can tell that this kid weighs more than that kid, right? And that would be an example of using a cantilever in static mode. So a lot of cantilevers in the micro world use the static mode of operation. pH sensors are done that way. You can use touch sensors, so you can look at forces on an actual microcantilever. There's intrinsic stress involved. You have two different materials in your cantilever. You put it in a different temperature environment. One material will expand more than the other. So it'll bend. Depending on how it bends, you know what the temperature is. That would be an example of a static mode. Okay?
Use piezoelectric for that too?
What's that?
Like a piezoelectric feedback on it?
Yeah, you can put a piezo-resistive element inside the cantilever. A Okay, and then if you stress the cantilever, that electrical property will change in piezo-resistive material, and you'll be able to tell how much stress the cantilever is under. Okay, so this is an example of a cantilever, a microcantilever. It's about maybe a few hundred nanometers across. The dot is gold. It's 50 nanometers across. Okay, this was done by the Craighead group at Cornell University. They were kind enough to give us permission to use this graphic. And they can actually detect the amount of gold in here by how the cantilever responds. And it actually, I believe this one is 6 attograms. Okay, so we talked about, micro, which is a million, right? What's after a micro? Nano, which is a billion. Pico, which is a trillion. Femto, I don't know, what's after a trillion?
A big number. Quadrillion, but
Right, it's 15 zeros instead of 12.
that's like 8.
Right, femto is 15 zeros, so 0.0000 15 times. Okay, femto.
18.
Atto is 18. So 10 to the minus 18 grams. Now, if you do the calculation, how many gold atoms is that? It's a lot of gold atoms. I think it's in the millions. So you can even go smaller than that, right? So attograms, a really small amount. The mechanical engineers do something called finite element analysis. So you can design a cantilever in the computer, apply the right physics to it, and see how it bends. So this shows you a cantilever that's being displaced by very small amounts. Okay? So that's an example of design. Using design, come up with a cantilever design to work. Okay?
On the base, RME, he had a program and we'd shoot our shots and it would show where all the stress was going to be at and how to reinforce when we shoot our shots. And
Okay.
it would turn right a program.
Yeah, so there's an old school way to do this.
Polarized.
You know how they used to do this stuff?
Polarized light.
They use polarized light and plastic. Yeah, you take lucite. Okay, lucite is birefringent material. So if you send polarized light through lucite, it'll rotate a certain amount. If you stress it, it'll rotate a different amount. So what they do is they put one polarized sheet underneath the lucite and another sheet rotated 90 degrees relative to the one underneath it. And then they'll stress the shape that they're interested in looking at. And you can see like a rainbow pattern depending where the stress points are. So a lot of these colors that you see is a holdover from those days.
Oh.
The engineers use the same color scheme when they do the transition from using those plastic parts and polarized light. They would still be able to understand what they're seeing on the computer.
They were actually looking at the spectrum then, but not anymore, right?
Yeah, they don't do it that way anymore because it's harder. You have to fabricate shape out of lucite.
Didn't you
And
have to
stress
heat
it.
it up or something? So that, or no, wait a minute, because actually the guy taught me right at the end of this hall, that's where I learned this the first time.
Mhm.
And because plastic stores stress, or some do, and they would heat it up with weight on it, and it would keep that stress in it, and then they could sit there and study it at leisure, basically.
You can induce stress into a material.
Yeah, something
Sure.
like that.
Sure. Okay, so we use cantilevers a lot for sensors. Okay, one of the primary applications of microcantilevers. It's probably used more for sensors than for anything else. So we can do chemical sensors for environmental and biomedical fields, health and safety, homeland security, those kind of applications. We can detect and analyze specific molecules or viruses in gas and liquid environments, okay? And we refer to the different types of materials that we're looking for as target materials or analytes, okay? So here's a probe coating. I think we talked about this last time, right? Quite a bit. So this is a probe coating. It looks green in this picture. It's stuck to the gold surface. We like to use gold because we can make molecules with sulfur on them, and sulfur sticks to gold. And we only put the gold in certain places so that the molecules will only stick in the places we want them to stick to. Okay, and we can design these molecules to have sulfur on one end and whatever we're looking for, the complementary part on the other end. Okay? So the trick is in the chemistry. Okay? So if you're working in a MEMS company that does these kind of sensors, there'll be some chemists that know all the black magic to make these coatings, right? And you can make a lot of money if you understand this stuff. If you like chemistry, go after this. You can make a lot. I'm not very good at chemistry. You know, I don't know a lot of chemistry, so I'm not going to pretend I'm a chemist. But I know a little bit to give you the ideas how it works. Okay? So we've got silicon nitride and then gold on top of that, and then our probe coating. And then the analytes or the target molecules that we're looking for will only stick to this probe surface. That's the idea. Some of these cantilevers are designed so if the analytes stick to the surface, it causes the surface to either expand or contract, so the cantilever will bend. That's in static mode. Other ones are designed so that if the molecules stick to it, you're adding mass to the system so it'll vibrate differently. And you detect the vibration as well. So there's two ways you can use cantilevers to see if the analytes have stuck to your cantilever or not. If they're present in that environment or not.
How's the vibration?
Okay, so gravity is not really a factor when you get very small. Okay? So we kind of disregard gravity. Of course, a big cantilever will bend because there's more mass to it. Gravity affects that more. A very thin and small cantilever, the force of gravity is small compared to the stiffness. So you won't see it bend or bend much. It has to be really long to see that on a micro scale. Okay? So here we see a probe surface, and here are the little purple analytes. They get into the surface, they get adsorbed, right? They become part of the surface, and they cause the surface to expand. So now this surface wants to be longer, right? If that wants to be longer, then it's got to bend. So it can compensate for that. If you think about it, it'll start to make sense. Okay, so bimetallic strips, we've all seen those. They're in thermostats. Well, maybe not all of us, but some of us have seen those. You take apart an old thermostat, you're replacing it with a digital one. Take it apart, the old one, you'll see a coil, and has two metals on it. And if you take a lighter and heat it up, you'll see the coil either unwind or tighten up, depending on how they designed it. And those bimetallic strips, what happens is one metal expands at a different rate in temperature than another. Okay, so if one is expanding more than the other, it's going to want to bend in the direction away from the one that's expanding more. Okay? So you can use that information to determine something about the environment. If you coat it with a material that, let's say the pH is higher, one material expands more than the other, then you can use it as an acid sensor. Okay. Let's go back. So if you heat the metal strip, you have two different coefficients of thermal expansion. That's the material property we talked about. Coefficient of thermal expansion. So if you raise it up by a certain amount of temperature, it'll expand by a certain amount. Usually it's a percentage of the length that you're heating. Okay? So, and the direction it bends depends on which material expands the most, which metal expands the most. So in this case, this material is actually contracting, so it's going to bend up. In this case, the material is expanding, so it bends down. Okay? Now, if we go to dynamic mode, well, before we do that, how do you detect if it's bending? Well, you can shine a laser beam and bounce it off of it, right? And the angle that it's reflected will be different, depending on how much it's bending. Does that make sense? We can actually take one of the little pieces of silicon and tape it onto the end of the cantilever and bounce a laser pointer off it. And when you bend it, you can see that reflected light move quite a bit. So you can actually measure very small changes quite easily, because when the laser hits the wall that's far away, it'll move a lot. Okay, so you can transmit it back. All right. Another way is by looking at the resistance changing. So we talked about that a little bit already. The piezo-resistant material layer can be embedded inside the cantilever. So when the cantilever bends, you get a change in resistance. And we can measure that electronically. So that's another way of measuring a change in a static system. Okay. You can create chemical sensor arrays, coating a multitude of cantilevers with different coatings, and then you can detect multiple things at the same time. Okay, you can multiplex your laser to scan up and down these things and look at the reflection. And when one of the reflected beams changes, then you know you just detected that particle. Okay? That's the basic idea on this picture. So I'll post all these slides, and we also have the written material so you can read through it later. Now you can go to dynamic mode, and that's what we're going to play with in class today. We're going to actually vibrate these things. Okay? So all systems like to vibrate at a natural frequency. Microcantilevers aren't any different. Bridges aren't any different. Everything has a natural frequency that it likes to vibrate at. And if you change the material, if you add weight or mass to the material, to the structure, you can change the way it vibrates. So we monitor the way it vibrates, what the natural frequency of the system is. We can use it as a sensor. That will make more sense as we go further in this unit. So you can get a microcantilever to vibrate by exciting it externally. So you can have an actuator on there that causes it to vibrate. Piezoelectric transducer you can use. Magnetic fields you can use if you have the right materials. Electrostatic was the most common. So you can get your cantilever to vibrate at its resonant frequency by changing the frequency that you're exciting it with. Once it matches, you'll see the maximum motion. And we'll do that. We'll actually break, we could go break a cantilever today. You guys like breaking stuff. Okay, so the frequency of oscillation is usually at or near the cantilever's resonant frequency. Any change in the physical characteristics of the cantilever, such as material, geometry, or mass, changes its natural frequency. So now we've got a measurable. We've got something we can measure. We see a change in that measurable, then we know we've sensed something. Okay? This is a difficult picture to see, but here's a cantilever. Okay? And it's vibrating back and forth. So here you see the cantilever, and then you see it blurring. Okay? And here it's a big blur. What's happening is the cantilever is vibrating back and forth and the end of it is moving more than the base. So I'm going to pick up this meter stick and show you what I'm talking about, right? I'm holding it in one hand. My hand's not moving a lot, but the end of it's moving a lot more. If I do it really fast, not very coordinated, it'll blur just like it blurs here. Well, the Sandians and the guys who work on microsystems and MEMS devices really like it when they can look at a blur envelope, they call it. It gives you an idea of how the motion is going and how fast it's moving at the end. So if you take a picture of a moving device and you leave the frame open for a certain amount of time, it will be blurry if it's moving. Okay? So by measuring that blur envelope and knowing how long that shutter's open, you can tell what the velocity of that material is. And we're going to do that too. We'll be able to figure that out using just a regular camera. Okay? So what changes resonant frequency? Well, mass usually does. Okay, a baby bouncing at the end of a diving board will bounce at a different frequency than an adult. Okay? And if you have a father and a baby at the same time, the frequency will change. The question is can you predict it? Right? Which would result in a higher resonant frequency, the baby or the baby with the father? So which one would resonate at a higher frequency? Think about it. Walk onto the end of the diving board. The baby would cause it to resonate faster than both the baby and the father together. And that's from experience. It's from a gut feeling. We're going to learn why in mathematics. So we actually have a video. Okay? There's the baby. Mama's going nuts. Help! My hair's going to fall in. He's having a blast. He doesn't care. Help me! Help me! Your mama's yelling. Oh, here comes the lifeguard or some guy picks up the baby. You shouldn't be doing that. Right? But you can see it slows down. Now this is a cartoon, right? We could have made it go the other way. But it's based on physics, so. And we're going to do that in class. So you want to see it again? It's kind of fun.
I like that.
So the guy who did this animation, his name's Fred. He was in the animation student here at CNM. And he won a national contest for Skills USA for animation. He got a gold medal. So now he's at the university, I think, in Massachusetts, studying graphic design and animation and all that.
That's how I ended up here, to cancel the program on it. And I missed the teach out on it.
Well, that happens.
Yeah, I noticed.
This is the mathematics behind it.
Oh dear.
It's not as complicated as it first looks. Okay, natural frequency of any system can be modeled or approximated by considering the system to be a mass on a spring. So K is what's called a spring constant. So think about springs you've played with. Right? You have very thick springs that are coiled up.
Mm-hmm.
Right? They're stiff. They're kind of heavy. Then you have very sloppy, floppy springs, like the ones that hold covers to jackets on. That, like the spring that's in your VCR cover, right? When you put the videotape in, that little flappy cover that always breaks, at least with me.
Pen?
And it has a little tiny spring that's very thin and floppy that holds it together. That has a very low spring constant, very weak spring constant. So imagine in your head, I've got a spring and I've got it attached to the ceiling, and I attach a mass on it. I pull the mass down and let go, it's going to bounce. It's going to resonate. If the spring is weak, is it going to bounce faster or slower? You have a weak spring.
Slower.
Slower, longer.
It may not even bounce at all.
Yeah, it may stretch it and stay at the bottom. But if you have a weak spring, that means K is small. That means your resonant frequency is going to be small or lower, right? K goes down, omega goes down. It goes down with the square root, okay? But it goes down.
It's like
Now, if I put more mass on the end of that spring, add more mass to it, is it going to go faster or slower?
slower.
Faster.
Okay, let's vote. Who says it'll go slower if I increase M?
Slower.
We got 4. Who says it'll go faster if I increase M? We got 3. Okay, now look at it. M gets bigger. It's in the denominator. So is 1 over 4 smaller than 1 over 2? Would you rather have a quarter of a piece of pie or half of a piece of pie? If you're not on a diet. You want the whole pie, okay. So if this is 2, right? 2 masses, that'd be like, let's say K is 1. Then you'd have 1 over 2. If you put 4 masses on it, then you'd have 1 over 4. Which one has a higher resonant frequency? Come on, guys. 1 over 2. Right, 1 over 2. So less mass vibrates faster.
Faster. Higher than that. That's like
So let's take another vote. Did I convert you guys?
Is that like Ohm's law where E goes up, I goes down, I goes up, E goes down?
Yeah.
Okay. Now it's set my understanding.
All right, so there's a balance here, right? We got to keep the equation balanced. So K is what we call the spring constant. That's how stiff the spring is. M is the mass. It's actually the mass of the spring, too.
Oh,
Okay? Not just what you hang on it. But if we assume a massless spring, it works out even better. Okay, if we look at the spring itself, what makes it stiffer and what makes it less stiff?
thickness.
What it's made out of, right?
Thickness,
That's E,
and then there's the thickness.
right? So E is what it's made out of. That's a material property. It's actually called bulk modulus or Young's modulus of elasticity. Okay, so that's why it's called E. How elastic is it? Okay, and E can be very complicated. Some materials have a different E in this direction than in the other direction, right? Think about plywood. Right? You glue on sheets of plywood. In one direction, it's more flexible than in another, depending on how the plywood's glued together. So E can be very complicated, but for our purposes, it's uniform. Okay, you have a uniform material, so don't worry about that. So you have a material property, but we also talked about, well, if it gets longer, it's going to change. If it gets wider, it may change. If it gets thicker, it may change. So the geometry plays a role too. So it's not just what you make the spring out of, but it's what shape it's in. So if you have an iron spring, like in the old days for the locomotives, you know, they have these giant springs, if you've ever seen them. Huge. You can jump on them all day, they ain't gonna bend for you. You've gotta have like a train car full of coal to get those things to flex, right? Well, that's because they're really, really thick. Okay, so K becomes very, very stiff. And there may be a short spring, not much L. So if L gets smaller, K gets bigger. T gets bigger, K gets bigger. The width gets bigger, K gets bigger. So you can change the stiffness, okay, by changing the shape of the material or using a different material. So when you start designing things in architecture, mechanical engineering, and microsystems, you can play with these things. You might not be able to change the material, so you can change the shape.
Does he have a numeric value?
Yeah, great question. If you look at the dimensions of E, you do a dimensional analysis, right? You've got meters cubed, meters for the width, meters cubed on the bottom, reciprocal meters, and you do the analysis, you'll find out that E is a pressure unit.
Oh, okay.
It's just confusing as well, right?
So, in theory, could you accomplish by adjusting those, so you could fit them like where you want them, accomplish the same thing, let's say a 2-micron
Sure.
nanometer as
You
you
can-
could with a 20-micron?
Yeah, you can change the thickness and the width, or just the thickness, or just the length, or the thickness and the length. You can do any combination you want to get a specific K. And you might have 10 different ways to get the same K, or 100 different ways, right? It just depends what you want, where you want it to fit. You may not be able to make it really long in your application, so you have to make it shorter. So if you make it shorter, then you might have to compensate with the thickness. Okay, so if you want to keep K the same and L has to be shorter, then thickness has to be thinner. Okay? All right, so we can change how springy something is by changing the material or the thickness, shape, geometry, and or by adding mass to the system. If you have a cantilever system and you add mass to it, you'd expect the frequency to go down. So you have a way of using it as a sensor for mass added. All right, I think we've talked about that enough. So, you asked the question about what units E is. It's in a pressure unit. If you do the analysis, you'll get pressures in the form of gigapascals. Huge numbers, right? Giga is huge. Well, rubber has a very low elasticity, right? It flexes really, really easily. A rubber band, you can't make a cantilever out of a rubber band. There's no way, right? So it's very, very low. Part of it's because of the material, part of it's because of the shape. Polypropylene's a little bit stiffer than rubber. Oak, right? Walking the plank. They use oak. Diving boards, old school diving boards, go along the grain. It has about an 11 gigapascal value for E. Aluminum alloy, oh, now we're cooking, right? Very stiff. We build things out of aluminum. And metal studs now, steel wood studs. Okay? Polycrystalline silicon, look at that. 160. Very stiff. Doesn't bend much. Okay? Diamond. Super stiff. Okay? So if we want something very, very stiff, we can make it out of diamond or polycrystalline silicon. And they make resonating structures now out of diamond, synthetic diamond. Okay? Diamond nonetheless.
So that's not a silicon that's seeded to any, it's polycrystalline, it's not crystalline.
Crystalline silicon is a little different than polycrystalline silicon. If you change the grain sizes in polycrystalline silicon, you'll get different E's. Because the grain boundaries play a role. In pure crystalline silicon, there is no grain boundary, so you get one number. You can't really change it.
Polysilicon and grain boundaries, right?
Yeah. Yeah, there's lots of little crystals kind of stuck together is a way to look at it.
Doesn't matter which, doesn't matter if it's a 100 or a 111.
It could matter what direction too.
Okay, but it's not going to matter that much, is it?
I don't think it matters in the case of silicon as much, but some materials it makes a larger difference.
Oh, okay.
And you might use that to make some exotic device, some exotic sensor.
If you use the wrong orientation, you can also break the cantilever, right?
Yeah, yeah. You break in different pieces, right?
Wang, there it goes.
That's good. Okay, so thinking back on that K over M, square root of K over M, which yields a higher frequency, a lower mass or a higher mass cantilever, if we leave everything else the same? Lower mass will give you a higher frequency because it's in the denominator, which yields a higher frequency, a short or a long. Remember K? The L was in the denominator for K. K is in the numerator. If we make it longer,
I'd say longer.
K would get smaller.
Then if it gets smaller, then it should go.
If L gets longer, K will get smaller. K gets smaller, the frequency goes down.
Down.
So will a short cantilever give you a higher frequency, or a long cantilever give you a higher frequency?
Short.
What's that?
Short.
A short one will give you a higher frequency. And we kind of know that from
Yeah.
experience, if you think about it. Okay, which gives you a higher frequency? A thin cantilever or a thick cantilever?
Thin.
Thinner one will give you a higher one?
Thick.
Thin.
Thick? Thicker one? Thicker one? Everybody say thicker? Okay, how many say thinner?
I say thin.
We got one for thinner. Dave's kind of hiding. He doesn't want to vote.
I remember doing this that one time in the class and I'm getting myself confused. When we gave it the rulers.
Well, what do you think? Thicker is going to be stiffer or less stiff?
Thicker's stiff.
Thicker stiff. Okay. So thicker stiff. So that's in the numerator of K. So K would go up. So the frequency would go up. So we get a higher frequency, right? Oh, but here's I'm going to throw you a curveball. If you make it thicker, the mass goes up too. The mass is in the denominator. So which one wins the race?
What's cubed?
It's cubed. Good.
Yeah.
All right. That's cool. So think about width. If the width goes up, it does get stiffer, but then it also adds mass. So the mass goes up. They compete. Which one wins the race? You're going to do that in class, okay? Okay, which cantilever material yields a higher frequency? Wood or metal? Assume everything else is the same. Metal. Good. Ooh, there are the answers.
Wood.
Wood? That's wrong.
I was going to say, wait a minute. Okay, talk about
Okay, for
curveball.
those of you who are listening to the lecture in the
Yeah.
future, metal.
Yeah.
Metal has the higher E, if we remember, right?
Yeah.
Doesn't it, like in wind instruments, aren't those the reeds like wood?
Yes, the reeds in a wood instrument are cantilevers.
Yeah.
Very good.
Well, you know.
Clarinets,
Yeah.
saxophones. They
Isn't
tie the reed down on one end,
Yeah.
right? And then what does the musician do? He makes it wet.
Yeah.
It changes the E because you're making it wet,
Well, not only that, but
and it vibrates differently.
you know, like from a saxophone to a clarinet.
Metal, the one vibrate like the wood,
It would vibrate, but different.
different.
Yeah, so you probably have to design your instrument differently. There might be metal reeds, I don't know.
Yeah,
Usually
yeah.
metal vibrate longer, right? Longer period of time.
Maybe, maybe not.
You can't change the property of metal like you can wood with saliva.
Yeah.
Right, you
Isn't
can
that
adjust the properties of a wooden reed a lot easier if you're a musician. You can actually shave some of it off,
Yeah.
right? Use a different length.
Yeah, from a saxophone to a clarinet, they're a different width and different length.
And they have different shaped reeds, and they use a specific type of wood to get you in the ballpark. So that's really good. That's a good example. The jaw harps, you know, the southern jaw harps where they have the different pieces of metal and they're tiny.
Like a child's voice, is it a different pitch than an adult's voice? Probably.
Well, absolutely. A kid's voice is a higher pitch because the geometry is different.
And
Materials are the same.
You know, because, you know, I mean, they don't, like, their little vocal cords are little, you know, and theirs are
Yeah, the vocal cords are different length.
It's kind of just
It's
a,
like a ukulele and a guitar.
yeah.
You got a shorter string and a longer string. You get different pitches. All right.
Wow.
So here's a cartoon of a dynamic cantilever. You can see we've coded each one with different molecules in this case, right? Different probe molecules. Here's a target molecule that's latched itself onto it. Okay, so you can create this array and you can vibrate them. So if you add mass to one of these cantilevers, the vibrational mode will shift. And we have a video. Okay, so we can see a flow of molecules going across the cantilevers, and then you'll see all of a sudden one of them change because it got stuck to that cantilever, that specific cantilever. Now, this animation isn't quite right. You wouldn't have these incoming beams bouncing. They would be stable. The ones coming off would be vibrating. Okay? So our animator made a mistake, and we didn't catch it right away. But it gives you the idea.
Kind of like with the mirror, you know, the light beam didn't change, but the angle did. Kind of like that.
Yeah, the angle of the mirror,
Uh-huh.
the reflecting surface is changing, so the light coming in will hit it at a different angle because you just tilted the mirror.
Mm-hmm.
And
You'll
the
see
light
it
coming
moving back
off.
and forth on it. It's staying in one place, but that's moving. You'll see the beam going across it up and down it. And that one side you're saying stays the same.
Yeah, it would be going
Yeah,
back and forth
it's-
across the.
We have to,
It's more like that.
well, it's a little bit better. These don't move as much, but yeah, you know, you look at the beams coming off of it, and the resonance or the frequency of the beam hitting the position-sensitive device changes, and you know you've detected something, that something stuck to one of the cantilevers. By looking at all the beams, you know which one has detected something. Okay? So here's your target molecule sticking to the surface.
Looks like they're doing
And
a
slow
fun
it
run.
down. And we can do that in class with big examples of that, macro models of that. All right. Atomic force microscope has a static mode or a dynamic mode. This one's actually more accurate. It has a finer resolution. So most atomic force microscope systems now use a dynamic mode where they tap on the surface. This is grossly simplified. A little more complicated than this. But if the cantilever is tapping on the surface, you can tell how far it goes until it hits the surface, and then it'll bounce back up again. Okay, so by looking at how this sine wave is transferred, you can tell what the surface looks like. All right, this is a static mode. Here I'm moving my sample, and as it moves underneath, this gets pushed up and down and bends. Okay, but it's really a static mode of operation. Right? It's not tapping up and down like this one is. All right, in order for the microcantilever and an atomic force microscope to have the sensitivity to map a surface on a very small nanometer scale, it needs to have a pretty low spring constant. It has to be flexible, so we're going to make them thin. The low spring constant allows it to respond to very small forces, like the force from an atom. Okay? Cantilevers must also have a high resonant frequency so that it doesn't begin to oscillate on its own. So you got to make them flexible but kind of stiff at the same time. Okay? So if the spring constant's too high or the resonant frequency is too low, the atomic force microscope cantilever wouldn't be sensitive enough. So you have these these structures, these dimensions to play with, as well as the material. Okay? So a spring constant on an AFM is about 1/10 of a Newton per meter. A slinky is about 1 Newton per meter, 10 times that. Okay, the higher the spring constant, the higher the frequency for the same mass. Atomic force microscope has a very low mass. So with the low mass, it has a high resonant frequency, even though its spring constant is low. Okay? Does that make sense?
And the speaking about the microscope, like on those new edges that they made where they have really deep grooves, are they able to see any type of grooves?
Yeah, that's a hard thing to do with the cantilever. So if you have a very deep trench and you want to probe down into it, what do you see? Right? I'm going to draw this on the board. This is a really good question about metrology and measurement. Let's say I have a square cross-section, a rectangular cross-section, very deep groove. If I want to look at this groove by tracing it with some kind of probe, okay, what happens if I have a perfect probe that's very, very thin and long? If I drag it across here, right when it gets to the edge, it's going to go down, right, see the bottom, and then come back up. So my signal is going to look like this. It's going to look just like the surface, isn't it? Because I have a very thin and long probe. Infinitely thin. As long as I need it. I can get a perfect profile, correct? Now the problem is in real life, no probe is that thin, right? It does take up space. So the probe, the tip of the cantilever, is going to add to the measurement of the surface, isn't it? So let's pretend
More like a wave than a trench.
well, what happens if it's a triangle? When it gets to the edge, it's going to do
How's that
this,
draw?
right?
Yeah.
And then it's going to move longer, right? It's really long. So as you're moving the sample across, the next step would be, right? The next step, oh, it gets caught up on this side, and then it starts riding up again, right? So if you follow the point, what are you going to get? You're going to get something that looks like the tip, don't you? It's going to look like a triangle trench, not a square trench. If your trench is wide enough, then you're going to see a trace on your machine that looks like this. It's going to be like a trapezoid. It won't be a nice square trench. The side of the trapezoid is actually telling you what the tip looks like. So when they make atomic force microscope tips, they have ways using etching of crystals to make a perfect step. Right? Perfectly vertical. So they know that this is perfect. And then they drag their tip across and they see how sharp this edge is. So if it's very sharp, then they know they have a good tip, and if it's not so sharp, has a defect in it, they know they don't have a good tip. That's part of the measurement system. So the measurement system actually adds into the uncertainty. Right? No measurement tool is perfect.
What's that tunneling electron microscope thing? Is that like, does it detect things like that, or is this like a different?
It's another measurement system. This doesn't have anything to do with cantilevers.
No, I'm just curious.
So the tunneling with an electron microscope uses a different method.
Okay.
Maybe we can talk about it another time. So, but the tip shape's really, really important to measure the surface. Now, when they're looking at very flat surfaces, like the surface of a crystal, and they want to look at the structure of the atoms, then they only use the very end of the tip, where you have one silicon atom at the end of the tip. And you take the surface, right? Also silicon atoms in this case. And these two atoms, the atoms interact. So you will get something, when you look at a 111, you'll see dots that are in the triangular shape. If you do a 100, you'll see dots that are in the right angle shape. And I have some pictures of that. But what's interesting is you see some other artifacts, too. You see little wing patterns. You see other patterns that aren't in the crystal. But that's because you've got two bonds on the silicon atom that aren't, two electron clouds that aren't attached to anything. And they're feeling along the surface, seeing the other electrons. So you do see the tip structure in a sense, even on that atomic scale. There's a really good paper on that. It's kind of
a static measurement rather than a dynamic measurement?
Yeah, this is more of a static. They're not tapping it. They bring it close enough. Well, maybe they use dynamic. I think they use dynamic on this, but it's very small motion.
Wouldn't it get better results by using a camera, those high-end cameras?
A camera?
Yeah, like where it reflects back to what's down there instead of using it with a tool.
Well, you have to use you can use X-rays and use an X-ray diffraction pattern to see the structure of the atoms. That's how they first did it. Because X-rays are very high energy photons, very short wavelength, and they interact with the outer shell electrons, and they get diffracted by the crystal. And then you can back calculate from the crystal, or from the diffraction pattern, what the crystal structure is. But if you're looking at surfaces, it's a lot harder to do that. If you're looking at both, then you shoot your X-ray through the crystal, see what comes out the other end. All right, so macro-sized cantilevers are similar to micro-sized cantilevers. How so?
Shape.
The way they react.
Where you put.
You make them thicker, longer, shorter. They react the same way. How are they different? Well, you'll find out that the frequencies are a lot different. If you make a miniature diving board, 100 microns by 20 microns by 2 microns, it's going to vibrate in the megahertz range. Really high frequency. If you make a large version of it, it's going to vibrate slowly. So that's how they're different. It's one way to do it. And how does a microcantilever bend compared to a macrocantilever? Well, if you're standing on a macrocantilever, you can make it bend just due to weight, due to force of gravity. You have a lot of mass. But on a micro scale, there's not much mass there. So it won't bend due to gravity, but it'll bend due to other things. You can't really use it as a diving board for a dust mine.
Yeah. You mean they don't have swim parties down there?
No.
Oh, darn it.
Okay, so summarize. Then we're done with this lecture and we can play. Microcantilevers are used for a wide variety of applications. The specific application determines its dimensions of the material you want to use. So you're going to design for the application. It's the cornerstone for a lot of microsystems devices. Okay, lots of applications, sensors, gallium force microscopes, micro switches, needles, probes. Okay, as transducers, where you're converting some environmental thing like stress, temperature, pH, force, when you're converting that into an electrical signal, you have a transducer. Transducer microcantilevers are operated in static and dynamic modes. So there's different ways you can run them. That's the basics. And then we don't guarantee anything I say is correct. Okay, that's what that says. So you can't sue me. This is the can't sue me slide.
Is that like that fast talk at the end of the commercial?
Yes, that's like the very fast talk at the end of the commercial. Okay, and those are the acknowledgements.